Okay, so here's a quick lesson on concavity. So a graph is called concave down when the second derivative is negative. And a concave down graph would look like this. A graph is concave up when the second derivative is positive. That would look like this. And a point of inflection happens where the concavity changes. So if a graph goes from concave up to concave down, at some point between there's a point of inflection, and that's what we're going to learn how to find right now. So it's a lot like relative extrema, except we're going to be using the second derivative instead of the first derivative. So here's a simple problem, and then I'll give you a couple other simple ones to practice. So we're going to determine the concavity and the points of inflection of this graph. So everything is based on the second derivative. So we're going to quickly find the second derivative. First derivative is this. And the second derivative is this. So to find the possible points of inflection, we need to figure out where this derivative is zero, where the second derivative is zero. So I'm going to set it equal to 0. I'm going to factor out as 60x squared. And we'll get the possible points of inflection, PPOI, at x equals 0 and x equals -2. Now, just like with the first derivative and finding out where it's increasing or decreasing, we're going to make a chart. But instead of using critical numbers, we're going to use these possible inflections. So the chart goes from negative infinity to -2, -2 to 0, and then from 0 to infinity. So now we're going to make a test point in each interval. So the first interval, I'm going to use -3. The middle interval, I'm going to use -1. And the last interval, I can use anything above 0, 10. And we're going to determine what the second derivative is at each one of those points. And that will tell us if it's concave up or concave down at each interval. So here we go. The first interval. If you plug in -3 into the second derivative, you're going to see that's a positive, -3 squared, times a -3 plus 2 is negative. So you're going to get a positive times a negative, which is negative. And I'm going to do the same thing now with the other two intervals. So if I plug in -1 into this second derivative, you'll get a positive times -1 plus 2 is positive. So positive times a positive, which is positive. And finally, when you plug in 10, you obviously get a positive times a positive, which is positive. So the conclusion is this. The graph is concave down where the second derivative is negative. So the graph is concave down on the interval -infinity to -2. And then the graph is concave up on the next two intervals from -2 to 0, and then again from 0 to infinity. And you can combine this interval to be just -2 to infinity. So that means the point of inflection finally is where the concavity changes. And the concavity went from concave down to concave up at -2, which makes -2 of a point of inflection. So we can now also say the point of inflection, POI, right? Inflection is at -2, comma, And it's the point on the original graph, so you have to plug in the -2 here. So you can do that with a calculator, which I'm doing right now. 3 times a -2 to the 5th plus 10 times 16. And I'm getting 64. So the point of inflection is at -2, 64. And you should check that with the graphing calculator. Just graph the original function and see if it looks like it changes concavity there. That is it. I'll give you a couple problems to practice, and good luck.